Today's class we discuss application of Gauss's law. Okay, so application. Okay, Gauss's law and its application. Gauss's law and its application. Okay. Now, first application is the cylindrical symmetry. First application is the cylindrical symmetry. So, what is cylindrical symmetry actually? So, you see that very carefully. Suppose there is a line. Suppose that is a line, straight line. Okay, and these line contain okay, and a positive charge. Okay, these line contain a positive charge. Okay, and that is a infinite line actually. Okay, that line is a infinite line, not here that is in that direction here in that. That is infinite long line. Right, a long wire actually, and these wire contain a positive charge. Now, if you want to calculate electric field sounded by that wire, by their object or line, okay. So, if you want to calculate that electric field, you need to apply the Gauss's law. So, choose a cylinder. We choose a cylinder. That's a cylindrical symmetry. Choose a cylinder. Okay, a cylinder, and these line passes through the cylindrical center actually. Okay, the cylindrical central axis, and now the distance is r radius. Okay, now we know that if that is a line or where, so get the lambda equal to q over l. Okay, so that length is now the cylinder choose, that is L, R radius, and calculate electric field like here or like here. Okay, okay, that's the surface of the cylinder. Okay, that is the surface of the cylinder. If these charge were contain a positive charge, so you know the electric field goes outward direction. That is a outward direction electric field. And we should consider the small amount of surface here, that is a delta A or delta S, if you choose any. Okay, this is the surface actually 3D. Okay, and the electric field goes outward direction E. Okay, and if this line contain a negative charge actually, if it contain a negative charge, okay, so electron goes inward direction. Okay, so this charge q is minus q, otherwise both are the same. So okay, and that is called cylindrical Gaussian surface, and this pink color line which is a Gaussian surface. Okay, and if I choose the Gaussian surface, to choose very carefully, because if you see that the radius, there is the radius r in all direction. If you choose the electric field in that surface here actually, so E in that direction, E in that direction, and that is the small amount of surface is delta A, and that is the radius r. On all direction you get radius is r. Okay, so now if we apply the Gauss's law here, okay, so we know that that is flux phi, and that is a E times dA, that is equal to charge enclosed. These are contain the q amount of charge, okay, enclosed by the surface, by epsilon naught, and the E dot dA, the small amount of, so if E in that direction, outward direction, so we know that A also in that direction, the A also in that direction, similarly A in also at that direction, so that is equal to E dA cos 0 degree. Okay, there is a closed surface, that is equal to closed surface. The symbol circle represents that is a closed surface indication. Okay, that is equal to Q enclosed by epsilon naught. We know cos 0 be the 1 and E is the constant. Suppose that is a dA and that is Q. See, that is the enclosed, obviously, epsilon naught. And integration dA you get a Q over epsilon naught. So what is the value of A? If you see that very carefully, and there is a cylindrical surface, I know that the area, surface area means a curved surface area of the cylinder, curved surface area of the cylinder, that is 2 pi r L. L is the length. Okay, we know that. Uh, so now replace that is a E A equal to 2 pi r L Q over epsilon naught. Okay, now that Q represented by lambda L, total length. Okay, total that is equal to, that is lambda times L by epsilon naught. So we get E equal to 1 by 2 pi R L lambda L by epsilon naught. If I cancel this length, so get electric field E, that is equal to 1 by 2 pi R lambda by epsilon naught. Okay, so if I choose a vectorical, okay, that is a vector. If I choose a E as a vector, that is equal to 1 by 2 pi r, that's the lambda by epsilon naught, and the direction is actually that is a, if that is r, so that is called a r cap direction, the same as vector. Okay, the box. And look at the equation. Okay, that equation doesn't depend on length. You see very carefully, that electric field equation, this equation doesn't depend on L. So if I choose any value of L, okay, let us go to the plus sign. See the plus sign here. Okay, this plus 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 plus. Okay. Okay, this equation doesn't depend on length, means independent of length. Okay, so very carefully. So that is a line charge, and the equation is E, electrically. So actually, what is the value of L? If I infinite any value of L, and doesn't care. Okay, that's the cylindrical symmetry. The application, first application of Gauss's law is very important. Board exam also, JEE and NEET exam also. Okay. Okay, so if that is somewhere, suppose these are the where contain, suppose a negative charge. Actually these where contain a negative charge, and I apply the cylindrical symmetry here. So electric field actually means the inward direction at that point, electric inward, because these lines contain negative charge. We know the electric field is inward. Okay, so if electric field is inward, so that actually the lambda is less than 0, means a minus q charge, obviously. Here if a electric field goes outward, so lambda obviously that is greater than 0. Okay, where it go to the plus? Okay, clear? That's a cylindrical symmetry. Next we discuss that the planar symmetry, second application. Okay, now write down some notes. Okay, some important key notes. In cylindrical symmetry, if you want to calculate electric field, if you want to calculate electric field surrounded by the charge wire by the charge where you must choose a cylindrical, you must choose an cylindrical Gaussian surface. Cylindrical Gaussian surface. And a charge of wire passing through the entire axis of the cylinder. And charge wire passing through the entire axis, the entire axis of the cylinder. Okay. Next application is planar symmetry. Planar symmetry. So what is a planar symmetry? The name planar is called plane or surface actually. So we consider a charge sheet. Charge sheet contain all positive charge. A sheet, very thin sheet. Okay. So if you want to calculate the electric field, so this thin sheet contain positive charge. Okay. So choose a suitable Gaussian surface. The suitable Gaussian surface now look like a parallelepiped. Choose a 3D or a 3D cuboid. Okay. These three lines are equal. Okay. This pink color line surface actually, this pink color surface is a Gaussian surface actually. This surface encloses the charge sheet actually, the thin sheet. And here I choose a small surface here in that direction, area vector. Similarly, a thin sheet, that's why A also in opposite direction behind the sheet. A positive and negative, that is a axis, that is a plus x, and here that is a minus x. Okay. So if I calculate electric field, if I apply the Gauss's law, same area, should I apply the Gauss's law? So we get epsilon naught phi E dot dA area vector, that is equal to Q charge enclosed by that Gaussian pink color Gaussian surface, parallelepiped surface. Okay, so now simple E, obviously there is a positive, so E that direction, and E also that direction, okay, outward direction. So both are in same direction, so cos 0, they are parallel, so E and D are parallel, so you know that that is a cos 0. So E epsilon or here actually no E, and here that dA integration is A for right side plus x direction, and that's A E A, that is a minus x direction. Both are here the same, okay, both area are the same. Now that's charge enclosed, because that is thin sheet, very thin means a very thin. Okay, that's why this sheet, the thickness is very small, so electron goes both in outward direction. So if you want to calculate electric field that thin, that small area, so actually calculate these two electric field actually, both front and back. So that's why these two electric field are, their magnitude are obviously same, but they are in opposite direction obviously, but the magnitude are the same. So if I calculate that these, so epsilon naught EA means get a 2 EA, that is Q enclosed, okay, and that is E, that is equal to Q by, it's actually enclosed, twice epsilon naught A, that is actually very important, that is not a vector representation actually, okay, that's only a representation of magnitude only, okay. Now see very carefully, and that is a surface actually. So get a surface charge distribution sigma, that is equal to Q by some area, that is Q equal to get a sigma A by twice epsilon naught A, so A cancel, so E equal to, here that is a sigma by twice epsilon naught, that's the magnitude of the E. And if you want to put a vector sign on E, that is also equal to E equal to vector sign, that is sigma by twice epsilon, that is say that, suppose say that r cap direction, obviously in that direction obviously, okay, that is the r cap direction, clear. That's why it's very important, the E is independent on x axis. So if you see the see the equation in very carefully, and see that that equation is independent of x on axis also, okay. So that's independent of area also. Similarly, we see that is also independent of area. Okay. So if you see the independent of x and area, if sigma plus, so E goes outward direction. If sigma minus, the E goes inward direction goes. So means that E plus, the charge sheet contain the positive charge, and if sigma minus, the charge sheet contain that negative charge. So if negative charge contain means E goes inward direction. Okay. If E away, sigma plus, E away, it's sigma plus, E towards each other actually, that is the minus sigma. Okay, that's very important. Okay. Both are electric field vector. And see that the application, okay, that's a very good application actually. If I just take it some minute, there is a two charge plate actually. If one plate contain positive, take an example, one plate contain a positive, and if I choose that another plate, these plate also contain a positive, these two plate contain a positive charge. So actually, and this gap is a very small gap actually. So the electric field in that direction due to that left side of plate, so left side of surface. So in right side surface, electric field in that direction, or that is about sigma of plus, that is a sigma of plus charge distribution, or sigma plus minus sigma 1. Okay. And if see that is same two charge plate, one plate contain positive charge and other plate contain negative charge. So actually E in that direction, sorry. E outward direction, that is of course sigma plus, that is sigma minus, and density is the same. Okay, actually, so and E minus in that direction, this charge. Okay, so same direction, where both charge plate are positive, so they are away opposite direction, and if one plus and other plate is minus, so the same direction, if that is a plus and that's a minus, so from equal to left to right, and that is a plus, that is minus, a left, right to left direction. And choose another plate, one is negative and one is positive. That's okay, if I choose another plate, suppose thickness of plate is like that. If I choose that some thickness present in that plate, if I zoom that, you see the thickness, and if you see that these contain a positive, here these contain a positive, this side contain a positive, and this side contain a negative actually. Okay, this set contain negative. Actually, don't know what is the charge here. If they are in neutral, so actually, if there is a neutral, means there is a minus charge here, plus charge here, and you see that electric field in that direction. But here in inside, electric field goes to in that direction. It will actually in that direction. Okay, so here we get that electric field, if I inside, starting from here, electric field is present actually, but in that case, if they are neutral, so these are okay. But if is that is not a neutral, these are only a charge, a positive charge body, and that is a negative charge body, and don't know what is the charge present here. The charge present is here. So actually, not present here means here this electric field is not like this. So here the electric field is 0, here also electric field is 0, so plus attract minus, that is equal to 0, and these plate contain only positive and these plate contain only negative. Okay, these two plate arranged look like this, they are parallel and very close, so we get an electric field like this. If both are in positive and very close, and with large conduction plate, okay, there is a excessive charge, will look like this, here it goes outward direction, and here is like this, a 1 plus and minus. Actually, that is a that thickness. Actually, this is the thicker plate. Actually, this is the thicker plate. This plate also with a thicker plate. Okay, this plate also with a thicker plate actually, and these two types of thicker plate and close to each other, so board like this. Okay, very thin plate. If I consider this is a plus relative outward, if I don't know what is this side, so outside middle electric will be the 0, and that is 0. Okay, there is some application of obviously, and last is called the spherical symmetry. Last topic we discuss spherical symmetry. Symmetry. Okay, so consider a sphere, and this sphere contain a positive charge. They contain a positive charge. contain a positive charge. Okay, and if you choose a surface outside that sphere, okay, outside the sphere, actually not look like a like this. Okay, very good. Okay. So that the radius is small r, and consider that is a capital R radius. Let's choose the capital R, and this purple color line is a Gaussian surface. Gaussian surface. Okay. So calculate electric field at the Gaussian surface. Okay. So very easy. So E dot the area. This area is a Gaussian surface area. dA phi. Sorry, that is epsilon naught. The charge enclosed is a Q. Okay. And now if I choose a E in that direction, obviously, and area vector, choose a small area similar, that is both same. So E A indicate over, okay, the Gaussian surface and charge enclosed Q, and that is E. What is the Gaussian surface? That is a sphere actually. Okay, that is a sphere. That is 2. So not 2. Actually, the surface area of the sphere is, you know, that is a 4 pi capital R square, the Gaussian surface. That is a, see, these are the Gaussian surface, and the charge enclosed, we actually apply the surface. So surface charge density here, the sigma, that is equal to Q by area, and that area is that this area actually. Okay, this charge contain the surface actually. The surface contain the charge. That surface area is there. That is equal to sigma A. So sigma A, and this A equal to 4. That is also a sphere actually. So 4 pi small r square, and get E, that is equal to sigma 4 pi small r square by 4 pi capital R square. This 4 pi cancel. Okay. Forget the extra here. Okay. So now put the extra here. So sigma by epsilon naught we get small r square by capital R square, that is it. And if you choose a vectorically, so r cap direction and r direction both are the same. Okay. So here you see that the r, this radius, the Gaussian surface, you choose the Gaussian surface, that is a much greater than the small r. Okay. This surface contain the charge. This surface. Now choose another surface. Okay, choose that another surface. uh, choose inside the charge sphere. And if I put, that is a call capital R. Okay, case number 2 actually. This is a case number 2. Case number 2. So capital R now smaller, much smaller than small r. And we see the very carefully, this is a gray color line, a gray color surface that doesn't contain any charge. Okay, so that epsilon naught, that is E dot dA Gaussian surface, that is a charge enclosed. So charge enclosed is 0. Okay, so E, that is equal to 0 actually in this case. So actually no charge enclosed by the surface. So no charge enclosed by the surface. And in electrically, the first case, there is some this Gaussian surface enclose some charges actually. And here that is equal to zero electric field. Here you get zero electric field. Here some electric field. Here some electric field. Okay. Now here there's some mathematics here. Sigma by epsilon naught. If you multiply it by 4 pi in numerator and denominator, 4 pi r square and r cap. So the 4 pi sigma 4 pi r square, okay, that means sigma area of charged surface. These are the area of charged surface, and by epsilon naught, that's the area of Gaussian surface actually. That is r cap. That is sigma by epsilon naught. Okay, so that is the area of charged surface. Gaussian surface 4 pi r square, and that is the r cap. And here that is equal to sigma by into times a area. Sigma times area, we get a charge q. So we get a q over area of Gaussian surface, that is a 4 pi r square. Actually, if I put 4 pi epsilon naught r square, and that is simple electric field. Yes. So if it is if E outward means Q greater than 0, means Q positive, and E inward, if E inward means sorry, Q negative. Okay. So in the Gauss's law application. So today in the class here. Thank you.